you. So today I'm going to talk about Colog, the composable contravariant Comonadic login library. I was on an adventure to explore how different algebraic concepts can be used to approach the login problem. And today I'm going to share with you the results of my journey. So a couple words about me. Currently, I'm working as a Haskell developer at the Holmusk company, and we're actually using the Colog library there for logging. And in my free time, I do open source work in my Kovanikov organization, where I maintain different packages and help Haskell beginners, mentoring them. So logging is a very essential part of a programming. I can't imagine writing an application without doing some logging. It's one of the useful ways to understand what's your program actually doing. But at the same time, it's actually a very difficult problem. It contains many parts. So what we in Haskell like to do when we meet a very difficult and big problem, we like to decompose it into smaller ones. So let's do the same thing with the logging. When we do logging, first we need to decide what we are going to log. Is it going to be just raw text, or is it some custom data type, message data type that contains structure, or is it just a map from keys to values? Then we need to decide where we are going to log. Are we logging just to terminal to see the result, or are we writing to file to analyze it later? Maybe we're storing our logs in database if we need some persistence, or are we just submitting them to external service, which provides a lot of analytics and metrics for us? Also, then we need to decide how we are going to format our output. Should it be just some plain text, or maybe colored text for better understanding, or JSON, so later tools can try to parse and introduce more structure. And at the very end, we need to decide the context. Are we working in the IO monad and changing the real world, or is it some pure logging, which we are going to see later? So let's see how we can solve these problems independently without worrying each other. So actually, Colog is already modular and composable on the package level. The idea was to introduce some fundamental abstractions and pieces and combinators, and they're in the Colog core package, which contains a lot of combinators and reusable. And the idea is that you can implement different backends using these abstractions. So I would like to show how you can use it with different approaches. And Colog library, it contains MTL and tagless final implementation, which works nicely with popular architecture patterns. There's also Colog polysemy package that contains the same implementation, but based on the polysemy extensible effects library. Just a proof of concept that the same ideas can be used in different scenarios. But of course, in real life, we want to be more practical. Today, I'm going to tell you about fancy and cool abstractions, but we actually have benchmarks. And the latest release, previous one, introduced a lot of performance improvements. We switched from time library to Chronos, and that's improved performance significantly. So we have repo for that. So the most fundamental type in the logging library is a log action type. It's a new type. It's parameterized by two type variables, the message data type and the monad. And it just stores the function from message to a unit in a monadic context. The idea is that when we do logging, we're never interested in the returning value. So that's why we are returning just unit. Logging was never about seeing the value. It's about changing the context, how we can, so we can observe later what's going on. So the important parts are the message, what we are going to log, and the monad, what we are going to change the context for our logging. And the simple example of such logging action is log string std_out. It's just a wraparound put string line function. It works in IO monad, and it takes string as a messages. This is one of the basic things. So the main idea is that in Colog, logger is a value. It's not some function from some library that you call to give some side effects. It's a value. And in Haskell, it's actually pretty convenient to work with the values. Function is something that you cannot change. It's written somewhere in the library. The code is static and fixed. You can introduce some dynamic behavior via type classes, but you can't do much with the code. But value, you can do a lot of things with the value. So, and we are going to do a lot of things. So that's why this approach gives us a lot of flexibility. But you might wonder, if it's a value, how can we use it? Well, at the very end, it still contains a function inside. So you can always, one of the simplest ways is to pass this value explicitly as an argument to your functions, unwrap it from the new type constructor, and then just pass the message to this logging function. But of course, you can store this log action inside your monadic context. So they're later extracted automatically, so you don't need to do this all manual wrapping and unwrapping. And later in the talk, I'm going to show how to do this. It's actually not that difficult. OK, so let's first talk about composability. The idea is that we are going to have some very primitive, very small, and basic log actions, and then we are going to combine them into bigger and complicated ones. This is a very common pattern and idea in Haskell, like which combinator libraries work. We define some combinators, we define some fundamental and small pieces, and then we create the bigger and more complicated ones from these smaller ones. And the first subclass is a semigroup. Semigroup contains this mapend operator or diamond operator, which takes two values of the same type and produces new value. The semigroup instance for log action looks like this. We have two actions, and we create new action that first runs the first logger over the message and then runs the second logger over the message. So that's why we can perform multiple actions over the same message. So here's an example. You have some action that prints strings to terminal, but you also have some action that prints strings to the file. So you can then you can configure them independently, and then you can just compose them together with a semigroup into one log action, and then you will print your messages to both to the terminal and to the file. So you don't need to worry. You don't need to write a lot of code that does a lot of things in one piece, just compose things. Next thing is a monoid type class. In addition to semigroup, it contains empty value, which is a neutral element for this mapend operator. And the instance for log action, just log action that ignores incoming message and does nothing. So basically, it's empty logger that does nothing. And this can be useful when you want to disable login in some piece of code. So for example, if you have a function where you want to disable login and you're not interested to see logs in that, just pass empty as a log action, and you don't need to do anything else. OK. Next, let's explore the contravariant family of type classes, which allows us to have even more composability and modularity. The first type class is a contravariant. It's actually very similar to the functor, which is a very common and popular in Haskell, and I hope a lot of you worked with it. But you can see that the types are slightly different if you see the end of the slide. So let's try to understand the difference on the example. Let's say that you have a flour, and you know how to bake a cake. So you can say that you can have a cake. This is a functor, because you can think of functor as a way of having things. You have flour, you bake cake, and you have a cake. But contravariant is about consuming things. So let's say you know how to eat cakes, and you know how to convert flour to cakes. So you can say that you can eat flour. Basically the same thing. So, and this is the instance of contravariant for log action. So you know how to log messages of type B. You have a function from A to B, and now you know how to log messages of type E, how that works. You are given A, you apply a function to get a B, and then you pass the B to your given log action. So this contravariant instance allows you to change the type of a message that you are going to consume. And this is useful for formatting of messages. Let's say that instead of printing just strings, you want to print some message data type, which also contains some text. But what we have now is an action that prints only strings. Like terminal is a really basic and low-level interface. You cannot print data types to that. You can print only strings. But if we implement formatting function, this format message, which takes message and produces a string, then we can use contravariant type class to change the type of the login message. We apply format message function to the action that prints strings to the terminal, and now we have action where we can actually pass messages. So how it will go into work? You are going to pass the message, a string and the list of tags, and then it will be formatted and as a string, and then it will be passed to the string action. It printed to stdout. So contravariant allows us to format messages. But there is also monadic contramap function, Because of the structure of log action, we have access to monad. And actually, all pure functions that I'm going to present here, they have monadic versions. And this allows us even more to create even more flexible interface. So you can compare the monadic contramap with pure contramap. The implementation is basically the same, but instead of pure function composition, we are using monadic fish composition. It's really convenient. So how it can be used? Let's say that now we have a message that contains not only a string, but UTC timestamp. What we usually want to do when we do logging, we want to show when this message actually occurred, what is the time of the message. But we don't want to call get current timestamp function every now and then and pass it timestamp explicitly every time. We want this to be automatically. We want the login framework to give this for us. So we can implement the withTime function that takes string and constructs a message. How it does it? It takes current time, and then it creates message from the given text and the current time. And then we can use semap_m function to create action where you will give a string, then it will call this withTime function automatically to produce a timestamp and create message data type. And if you have an action that can log messages, then you can have messages with a timestamp, and it will be doing automatically every time for you. This is pretty useful. Semap_m allows you to attach different monadic things for your message on the fly. The next useful thing is actually a filter. So let's say we have a predicate that tells what messages we are interested in. And if you have a log action of messages, you can create new log action that will perform logs only for those messages that satisfy the given predicate. Let's see how this function can be useful. Now we have a severity data type that tells us how important the message is. So our message data type now contains not only the text, but also this severity level. So you might have some debug messages that are useful during development to see what your program is actually doing. And then you also have error severity, which tells us, OK, this is a critical error. You need to pay attention to that. So when you're developing your application, you might be interested in seeing all messages to understand what actually is going on. But when you give your application to users, you don't want them to see all logs, so they want to see this noisy output. So you might want to filter only messages that has severity warning or higher. Other input is not interesting. And that's how you can create new log action. And the idea here is it's actually lazy and composable with the rest of the functions. Because if you have in your log message std_out, if you have different functions that do some heavy I/O or do formatting, if your function doesn't pass filter, if it doesn't pass predicate, it will just won't be called. So you won't do extra work if you don't satisfy the requirement, and it will save you some time. It's also pretty convenient and in the spirit of Haskell. OK. So next type class is a divisible type class. It tells you how to split one part into two smaller parts and then handle those parts one by one. So for example, let's say that you have 8 hours of your work day. And during your work day, you need to do actual programming, but you also need to read some news like Twitter or Reddit. So if you have some function which will tell you how to split your time in between these two actions, then you know how to spend your whole working day. The conquer function is a neutral element for the divide operation. In our example, this means that you can always do nothing during your work day, and this still will be a valid working day. So the divisible instance for log action is pretty straightforward. The conquer function is the same as mempty. It's a log action that does nothing. But the divide is also very simple. We have a message of type E. We apply function f to have a pair of B and C. And then we first log the part B with our first log action and the part C with the second log action. So how this can be useful? Let's say that you want to print very compact output to the terminal, but to the file you want to print more verbose output to analyze it later. So you can just split your message type in two parts you're interested to see in the terminal, and the other parts to go to the file, or something like that. Next type class is a decidable. So it's similar to Divisible, but it has a function from A to either B, C. So let's say that you have some money and you want to buy a house or car, but you can afford both. So you need to decide what you are going to buy. So you first decide what you are going to spend money for, and then you can say that you know how to deal with your money. The lose here means that you can always burn your money and throw the ashes into the void, but we all know that it's just absurd. So decidable is similar to alternative because it allows you to handle only one cases. Not both actions will be performed, only one, while divisible will perform both actions. So, and the decidable instance for log action is also pretty straightforward and simple. For choose, we do the same thing as for divisible, but we handle only one case, and the either function. OK, so how it can be useful? We can actually implement our filtering function using decidable type class. So the type is the same, and the behavior is the same, but the implementation is different. So we can use choose to say that what message is going to do. Yeah, another example is that let's say that you have some non-important messages with a severity level, and they're going to go into terminal. But if you have a very important message, like error, then you want to send an email to your tech team, so they will fix this error message. So you can use this choose function to tell how to handle different cases and different messages. This is like dispatching of output to different sources. OK, next part, the most fun part, is how we can use Comonads in the logging framework. So this is a Comonad type class. It's very similar to Monad. Again, very familiar to most Haskell developers, but the errors are reversed. Unfortunately, Comonads are not that popular, and they don't have many use cases. But turns out that they can actually be used to approach the logging problem. And for our reference point, we are going to use the Comonad instance for the function arrow. So if we know that the argument of a function is a monoid, then we actually can implement Comonad instance for the function arrow. How it works? Extracts takes a function from A to A and needs to return A. Well, the only way to return A is to just pass some m to the function. But we know that the m has a monoid instance, so we can always pass empty. The duplicate function, given it takes a function from m to a, it needs to produce a function that takes two m's and it produces one a. But again, we know that the m is a monoid, so we can squash these two m's into single one and pass to our given function. So this is how the instance works. Well, because of the log action data type structure, we can't implement Comonad instance. It just doesn't have the proper kind and proper structure, but it doesn't mean that we cannot enjoy Comonads. We can implement the same interface in the same spirit. So the extract contains it has the same implementation. We have a log action, and if we know that our messages has a monoid instance, we just pass empty to our action, and that's all. We handle the message. The duplicate is slightly more interesting. If we have a log action that can log single message, then we can have a log action that logs two messages. It's also not that difficult. We just combine those messages together if we know that they have a semigroup instance and pass to our given log action. So it means that we can log many messages at once. But again, why stop at two messages if we can have any number of messages from 0 to infinite lists? So we can implement this multiplicate function, which constructs log actions that can handle any foldable of messages. It's the same as the duplicate, but we have a foldable of messages potentially containing maybe, it can be maybe or list. And then we can just fold those messages into a single one and log them all at once. So let's recap all our abstractions. The semigroup allows us to perform multiple actions over the single message. So it's basically like multiple dispatching of concurrency. The monoid instance gives us empty log action that does nothing, and this allows us to disable logging. The contravariant allows us to change the type of the login message, and this is useful for formatting messages. Divisible allows us to split our message into smaller parts and handle them independently. So this gives us even more modularity. The Decidable instance allows us to choose how we are going to handle this message. So this can be useful for filtering or for redirecting output to different sources. And Comonads allows us to squash many messages into a single one, and instead of performing multiple potentially expensive login actions, we can perform only one. Just need to combine. This is useful for optimization. So these type classes that I enumerated here, these are very abstract and general type classes. But if we apply them to the login problem, they actually solve real practical problems that we face every day. And it just feels warm and nice when you can see how these abstractions can be used, because these are not some ad hoc type classes which are implemented to introduce some overloaded names. These are well understood type classes that have semantics attached to them, they have laws. So they have ecosystem around them, and you can enjoy this ecosystem if you implement these instances. So it just feels that you are moving in the right direction if if you are doing these things. And again, it's really nice how different abstractions can help us to solve different problems. Okay, now I'm going to tell how to integrate this whole log action data type into your application, because we want to enjoy all these type classes, all these functions, all these combinators, but at the same time, we don't want to do a lot of work to pass this log action explicitly. It's nice to have abstract and nice and sound library, but at the same time, we want to have convenient library. It can be used, and colloc actually can be very convenient. So first, what you need to do is to create environment that will store your log action. This environment is parameterized by the monad, which we are going to instantiate later, and it contains different parameters for your application, like ports or different maps, like sessions. So this environment contains parameters for your application, but also contains the log action, which is parameterized by the same type variable m. The message data type here is the message from the colloc library. Colloc already implements a lot of functions and a lot of data types, so you can use logging with little effort. So if you just need to enable logging, it can be done very quickly and very easily. The first step is to introduce the log action to your environment. The next step is to implement the hasLog instance. It has three type variables. It's environment, the message data type, and the monad m, where we are going to log. This is a length-like data type. It has getter and setter, basically. In order to implement this instance, you need to tell how to get the log action from your environment, and need how to set. So you can change your environment, use a new log action, and apply all the functions that we introduced earlier to the log action inside your environment. So you don't need to pass this environment explicitly, and you don't need to pass log action. Just store it once in environment. You stir how to get from environment, how to set, and move further. And the next step is to implement your application monad. So here is the somewhat common reader T pattern. We have a reader T transformer. It contains environment parameterized by the same monad as we introduced just now. So reader T with environment for our application, and on top of the IO monad. And we need to derive a bunch of instances. So they can be derived automatically, so you don't need to write all that code to enjoy the logging. And the next part is actually using the logging. So let's say we have some handler that sends SMS messages. But while we're developing, we want to log the message with the debug severity, what phone we are actually sending. And this function, it takes phone and returns nothing but in monadic context m, and it has two constraints. Monad SMS, which tells us how to send SMS, and this withLog type class from the colloc library, which says that this monad m has access to environment that can log messages. And this log function, it comes from colloc package. So this basically tells us how to integrate. It's not that difficult, and the idea here is that it plays nicely with common programming patterns in Haskell. And here's the output with the default settings. So in Colog, we have a colorful severity, which helps you to tell difference between different messages. We have a timestamp. We have the line number of the source code. So it's also usually important to see where this login happened. So we have module name, and the function name, and the line in the code. We also have the thread ID, which tells us what thread it prints. Also may be useful in concurrent case when you have multiple threads that do logging and you want to see. And actually the message itself. So the output might be a little bit verbose, but it helps. And again, as I said, you can always implement different formatting functions. You just need to plug in this little piece, change formatting function with another one, and you will have different formatting in the way you want. OK, so Colog is a very young library, but it's been here for a while, and it contains some ecosystem around it. So there is main Colog repository, which contains 4 core packages, which I mentioned at the beginning of the presentation. They are maintained by our organization. And there is Colog sys package, which is a syslog implementation on top of the Colog. I was also surprised to know that there is actually Scala implementation of the Colog ideas. So they were adopted in different language, and you can see the implementation in the Scala Colog package. There is also a freeware repository, which contains a template for Haskell production level applications and uses Colog as a login library. So it shows how to use login like more production application, bigger example. You can check this out as well. And actually, there is my blog post about the Colog library where I describe this library in more details and show different aspects. There can be many more things can be done. With these instances, we can have combinatorial library. It allows us to do many cool things. So that's all. Thank you for your attention.